It's a pleasure to introduce our next speaker, Miguel Abreu from Lisbon, who will talk on toric geometry in Kaehler metrics and contact topology. Thank you.
Well, thank you very much. Good morning, everybody. Thanks for being here. Thanks a lot to the organizers for the invitation to participate in this very nice conference. Visit São Paulo again. It's always good to be here. So the purpose of this talk is to illustrate in a particular context how toric manifolds, which form a very particular but yet interesting class of manifolds, can be used for explicit hands-on constructions in some areas of mathematics. In this case, I'll focus on Kaehler geometry, and then towards the end, a connection with contact topology, following a road that I've been traveling for in my work for at least probably 20 years. So let me start with linear algebra, a little bit of linear algebra. So I come from symplectic geometry, so my base is always a symplectic manifold or a symplectic vector space. So I already screwed up. Sorry. Pressed the wrong button. But I think I know how to solve this. I've tried. There we go. So I'll try not to press the wrong button again. So we start with a symplectic vector space, which is a vector space of even dimension with a skew-symmetric bilinear form, which in a canonical basis is given by just the skew-symmetric 2n by 2n matrix, which I'm writing in block n by n. Okay? So in this linear context, what's a Kaehler metric? For me, it will come from a complex structure, linear complex structure, which is compatible with the symplectic form. That means that it has, when you combine the symplectic form and the complex structure like this, you get a metric, symmetric, bilinear form, positive definite. Well, it turns out that the space of all compatible for all such complex structures can be conveniently parameterized in this form. You pick any two symmetric n by n matrices, R and S, take S to be positive definite, and form these 2n by 2n matrix like that. Any compatible complex structure has this general form. You can check if you don't want to follow so much the lecture. Try to square this matrix and see that you get minus the identity, indeed. And if you combine it with the symplectic form, you do get a positive symmetric bilinear form. Now, this is too complicated, so let's assume that in this parameterization, I take the R to be 0. I just keep the symmetric as symmetric positive definite S. Then this J has this much simpler form, which is much easier to see, whose square is minus the identity, and when you combine it with the symplectic form, you do get a metric, which is just has this diagonal form, n by n blocks, with the positive definite symmetric real matrix here and its inverse there. So this is a particular class of metrics on a symplectic vector space. Now suppose you go to a local chart on the symplectic manifold. So symplectic manifolds have no local invariants, so I'll assume I have a local chart in R2n where the symplectic form is standard. I'm using symplectic coordinates, so the symplectic form is a standard symplectic form. And then compatible matrix of this form will be, again, of the same type, and now this matrix S changes from point to point. Depends on the x's and the y's, which are the coordinates I'm using in R2n. So that's still too complicated. So let's assume that it only depends on half of the coordinates. I'll assume that it depends only on x. It does not depend on y. So if independent of y, then when is such a thing, this is an almost complex structure, when is such a thing a complex structure, hence a Kaehler metric, you need this complex structure or this metric to be, the complex structure to be integrable. Well, the integrability condition takes a particular nice form. It is integrable if and only if the symmetric positive definite matrix is the Hessian of some function. And so I'll call this function which is defined in this neighborhood U with values in R, the symplectic potential. So it has to be a convex function so that its Hessian is positive definite. So once, if you have such a, I left the arrow there. Let me move it away. Oh, shit. Okay. So if it is indeed, if it has that form, the Hessian of a function, then, for example, you see the, no, it's here. Yeah, forget about that. The holomorphic coordinates are just this change of coordinates. The first derivatives of S will give you the holomorphic coordinates. And a particular thing that interests me is how the scalar curvature can be expressed in terms of that symplectic potential. And it has one nice form. The scalar curvature of that Kaehler metric can be written in this way. So I'm going to write it there because we'll use it. So this matrix S upper JK is the inverse of the Hessian of the symplectic potential. And then in each of its entry, you take the first derivative with respect to xj, and then another derivative with respect to xk, and then you sum all of them. That's what's meaning there. So the scalar curvature is this. Okay. Okay, and the point of me explaining this is that this local description of a very particular class of Kaehler metrics in local coordinates, so it was particular in several ways. I made R equal to 0, and I made S only depend on half of the coordinates, actually becomes a global description for all toric Kaehler metrics on toric manifolds. Okay, and that's what I want to explain next. And that started, at least from my point of view, by finding this paper of Victor Gilman of 1994, and then I started working on this around 1998. Okay. So what's a toric symplectic manifold? Toric symplectic manifold is a symplectic manifold, so even a dimensional manifold equipped with a closed non-degenerate 2 form, and with the Hamiltonian action of a torus of half the dimension. So an injective homomorphism of a torus of dimension n inside the Hamiltonian, the group of Hamiltonian diffeomorphisms of the symplectic manifold. So this action, each of its S1 pieces is generated by some Hamiltonian function. And if you put together the n Hamiltonian functions that generate the torus action, you get what's called the moment map. You get a map from your symplectic manifold to Rn. You see that these must be very special functions. They generate circle actions, all of them, and they commute with each other because they, in terms of Poisson bracket. So they are very special, and indeed, this puts a lot of rigidity on the image of this map, the moment map. And it turns out that the image of this map is always a finite intersection of closed half spaces. So it's always expressed as the intersection. Let's assume that D is the number of half spaces, and the half spaces are determined by a normal vector to the hyperplane and a real number which tells the position of that hyperplane with respect to the origin. So they are determined, the image is determined by a bunch of inequalities where this affine function, which is just determined by a normal vector to the hyperplane and the real number, and you require these inequalities to be greater, the points to be greater or equal than 0, so that you are on one side of these half spaces. So what I'm saying there is that the image is going to look like that. So in R2, you have some hyperplane. Here is the normal. It has some position with respect to the origin. Here is another hyperplane, interior normal. And you could have more. So the image will look pieces like this. We'll have some pictures in a minute. Okay? Now, it turns out that the pre-image of the interior of the image of the moment map for interior points, those correspond exactly to the points where the torus action is free on our symplectic manifold. And actually, globally, you get that on your manifold M, that part, which is the pre-image of the interior of the image of the moment map, is open and dense on your manifold and can be expressed as the interior of the polytope cross the torus, because the action is free across the orbits. And moreover, you can choose this splitting so that you have coordinates x and y such that the symplectic form is standard all over this neighborhood, which is an open dense part of your toric manifold. And these are called action angle coordinates. So you have kind of a big coordinate neighborhood which is open and dense on your toric manifold and where your symplectic form is standard. And so we are in that setup that I described a minute ago. So that means that, or at least on this whole open dense piece, any compatible complex structure could, well, you can express compatible toric complex structures in that form as the Hessian of a function, and it turns out that all, you can choose the coordinates x and y so that all complex structures have that form. So any toric Kaehler-metric or toric compatible complex structure will arise as the Hessian of some function, some symplectic potential defined on that interior of the image of the moment map. Now, of course, we want to look at complex structures that now extend to the rest of your manifold. You don't just want them to be defined on that openness piece, you want them to extend smoothly to the whole toric manifold, and that puts full restrictions on your symplectic potential when it approaches the boundary of the image of the moment map. And these turn out to be exactly the conditions. So your symplectic potential has to look like a piece of this type. So these are the affine functions that define the boundary of your polytope. You look at symplectic potentials that look like this. Sum of all of them, Lj log of Lj. And then you can add to it any smooth function on the closed polytope, or the closed image of the moment map, so that the Hessian of this thing is still positive definite, so that you are in that setting. So this is a way of parameterizing these things. So here is a simplest example, let's say. Suppose that the image of the moment map is just the positive axis in R. So n is equal to 1, and we are describing R2. This is the image of the moment map, of the standard moment map, 1/2 of x squared in R2. So look that here I'm illustrating the moment map. This picture is just topological, it's not a metric picture. Here is the moment map. The pre-image of the vertex is the fixed point, it's just the origin in R2. And the pre-image of all the interior points are circles, the orbits of the circle action I'm considering. So here is R2 and the moment map to R. So in this case, the polytope is defined by just one inequality, x greater or equal than 0. And so if you just look at the potential with 1/2 x log x, just don't add anything else, you compute the second derivative, which is the Hessian, and you get a metric which has the Hessian and the inverse of the Hessian. And this is the flat metric in R2 expressed in action angle coordinates. Okay? It's just usual flat metric, linear metric. In these action angle coordinates, it looks like this. I want to go. Okay. Now, I want something that will be relevant for this, is that suppose instead of considering x greater or equal than 0, define the inequality with putting here divide by some constant number, x over alpha greater or equal than 0. That is still some real number, positive real number. That is still the same, defines the same region. And my point is that when you do that, what you are introducing is a conical singularity at the origin of the metric. So this metric now, when you consider x over alpha instead of just x, you look at this again, you take the Hessian inverse, and the metric in all this red picture here is a metric picture of what's happening. You are getting a metric with a Cones angle singularity at the origin, and the angle is pi times alpha. So when alpha is equal to 1, the angle is pi, and you get the smooth metric. But if alpha is smaller or bigger than 1, doesn't matter, you get conical sat metric in action angle coordinates, and those will appear, okay? So for example, let me now describe a compact example. The picture is for CP2. So CP2 is a 4-dimensional manifold. The moment map for some torus action on CP2, which is the standard one, goes to R2. And here is the image of the moment map for CP2. Actually, the pre-image of these 3 edges are precisely the 3 standard CP1s, coordinate CP1s inside CP2. The interior is where the action is free. And if you just do the standard symplectic potential, not adding anything, so the terms corresponding to the coordinate hyperplanes, and then one term corresponding to this hyperplane, you get exactly the symplectic potential of the Fubini-Studi metric in CP2. Here is another example. Now, fourth example is when you add these kind of cone angle singularities to these terms. And this example actually relates to the talk of Rui Roger Fernandes on Monday, when he talked about Bochner flat Kaehler metrics by Robert Bryant. And in context of CPN, he constructed some Bochner flat metrics on CPN with cone angle singularities along in the normal directions to the coordinate CP1s inside, CPN minus 1s inside CPN. And this is how it looks like. Actually, so this is the first example where if you just take the canonical piece of the symplectic potential, you don't get any interesting metric unless all these alpha j's would be equal to 1, and then you would not have cone singularities. But it turns out that if the alpha j's are different from 1 and different from each other, you have to add another term, which in this case turns out to be also of the type L log L, but this L is now the sum of all the functions, the affine functions that define the polytope. And if you do that, you will get a Bochner flat Kaehler metric, which in this context, in this toric geometry context for these manifolds, I will characterize as an extremo Kaehler metric. I'll come back to it, to the definition of an extremo Kaehler metric. But these are Kaehler metrics which in this action angle coordinates have scalar curvature, which instead of being constant, is a first-degree polynomial. So it's a fine function of the coordinates on your moment polytope. And so in this case, just for completeness, here is the scalar curvature of this metric, has a constant part plus a first-order part, which is only different from 0 if if you have different weights on the different facets. Okay? And also this is a conical extremo Kaehler metric on CPN. So these include extremo Kaehler metrics on weighted projective spaces. So weighted projective spaces for rational values of these alphas arise, the Bochner flat metrics of Robert Bryant arise here for rational values of these alphas, but you could construct them for real values of the parameters. Okay, so just so that you don't think that any metric that you could think of could be written explicit in these terms, let me tell you which actually what was my main motivation when I started working on this. I really wanted to see explicitly the Kaehler-Einstein metric on CP2 blown out at 3 points. That's probably the simplest Kaehler manifold that admits a Kaehler-Einstein metric, and I don't think that anybody has seen it. Okay. And my goal was to see it. And I still haven't achieved that goal. Okay? So it will be determined for sure, it's a toric metric, it will be determined by a symplectic potential, which has 6 terms corresponding to the 6 edges of this polytope, plus something, and I would like to say explicitly that something. Never been able to. Okay? But explicit things only go so far, but they will go. I'll come back to explicit things. Let me now just tell you about some general results which are not so explicit. So the first is the work of Donaldson on this equation. So it's the scalar curvature in this setting with action angle coordinates, the scalar curvature being equal to constant. And he used this setting, this action angle coordinate setting, to prove in 2009, so before all these more recent developments regarding constant scalar curvature metrics, that a K-stable polarized toric surface admits a constant scalar curvature Kaehler metric. And the converse is due at about the same time to Zhu and Zhu, in about the same time, a bit earlier, 2008. This was 10 years ago. This was 2009. And so for toric surface, we know precisely, and this stability, this stability property can be read off from the polytope of the toric surface. So we know exactly when these things have or do not have constant scalar curvature metrics. And this was done using, it's a geometric analysis result done using this action angle coordinates approach. Of course, we cannot see this. We don't, most of them we can't see. So, for example, it applies to CP2 blown up at 3 points. And what is the metric? How? No way. Okay. Now let me describe another situation, also in dimension 4, and now for scalar flat solutions in dimension 4. Again, via some work of Donaldson, which generalized the construction of Joyce. And this comes because of the following reasons. So it's very specific to dimension 4 and 0 scalar curvature. Because in dimension 4, scalar flat is equivalent to anti-self-dual, and Ricci flat is equivalent to hyperkähler. And every time you see these kind of self-duality things in dimension 4, you can use holomorphic methods. There is a whole bunch of methods that appear that you can use to construct these things. And so, okay, I don't want to press the wrong button. Good, this was the right button. And so there is a long list of people that use these facts to construct explicitly Ricci flat metrics and so forth in this dimension 4. So Gibbons-Hawking, Hitchin, Kronheimer, Lebrun, Joyce, as I mentioned. A very relevant work from what I'm talking here is a paper by Calder, Beck, and Singer. Also Donaldson. And Donaldson, what he did was used action angle coordinates in this fact in dimension 4 and 0 scalar curvature to generalize the known Taub-Nut metric in R4 to a one-parameter family of metrics which are asymptotic to Taub-Nut in R4 but are not Taub-Nut. And what I did in 2012, it was published in 2012, with my colleague in Lisbon, Rosa Sena Dias, was to generalize this Donaldson thing that applied to Taub-Nut in R4 to all the toric non-compact manifolds where this thing made sense. So, and I'll give you a bunch of examples where it does make sense, but what we prove is that forget about the strictly, an unbounded or non-compact symplectic toric for manifold admits an asymptotic locally equivalent scalar flat Kaehler metric, and now this is the interesting piece, and a two-parameter family of complete scalar flat Kaehler metrics asymptotic to generalized Taub-Nut. So that means what Donaldson did in R4 can be done for all toric for manifolds where this thing applies. And if the toric for manifold has 0 first Schoen class, then you also have some statement about Ricci flat metrics in this family. And this construction is explicit. Explicit in terms of the PDE that we are solving. It's explicit up to inverting an algebraic function, which is not explicit. Okay? But the PDE is out of the way, so you can find by some construction explicit solutions of the PDE, which you see, but to write them you have to invert an algebraic function, a 2 by 2, an algebraic function from R2 to R2. And that is not always explicitly possible to do. But that is the context of this theorem. Let me give you here a family of examples, just one of the families. One possible examples. Here is the picture. So this is the moment map image of the quotient of C2 by a ZP action with fixed point at the origin. Okay. So this is the image of an isolated singularity in C2 at the origin, corresponding a cyclic quotient singularity over the P. These things admit resolutions, which are well known. And here is the moment map image of that resolution. You replace the origin by a sequence of blow-ups, so there are some spheres here, and I'm telling you exactly what are the normals to the facets that you have to add. So you kind of interpolate between these normals 0, 1 and P1 to this family of normals. Okay? Notice, and I'll come back to this, all of them have last coordinate 1. So that means that all the normals lie on a line in R2. And that is kind of the condition for knowing that this manifold R actually has first Chern class equal to 0. And I'll come back to this. So you can read the first Chern class, of course, from the moment map image. And first Chern class equal to 0 is determined by a condition like this. The normals lie on an hyperplane. Okay, so this is a non-compact toric symplectic form manifold, which is the resolution of this singularity. And this theorem gives you these families of metrics explicit up to inverting a algebraic function from R2 to R2. So these families of scalar flat Kaehler metrics and Ricci flat Kaehler metrics in these constants. Okay. Now let me come back to really more explicit than up to inverting an R function. Totally explicit things. And this is the family, which is much older than when I started working on this. Actually, I can do this more one. This is the family of metrics that Calabi in 1982 used to construct the first examples of non-trivial extremal Kaehler metrics. So let me say just a few words what are extremal Kaehler metrics. Extremal Kaehler metrics are critical points of a function on the space of Kaehler metrics on a complex manifold. That function is the integral of the square of the scalar curvature. The integral of the scalar curvature on a Kaehler manifold is a topological invariant. So you take the integral of the square of the scalar curvature, and critical points of that functional on the space of Kaehler metrics on a fixed cohomology class are called extremal Kaehler metrics. Constant scalar curvature Kaehler metrics are extremal Kaehler metrics, are critical points. But some manifolds, people know, do not admit constant scalar curvature Kaehler metrics, but they do admit extremal Kaehler metrics. And the first examples when Calabi introduced this notion were cohomogeneity 1 examples that he constructed. And let me describe in action angle coordinates in this setting what that family is. And let me make a picture first so to illustrate these formulas here. So you start with, in principle, R4, which means from the moment map image, you start with the positive. I'm doing this in R4. This actually could be done in Rn for any n. But let me restrict to R4, which means from the moment map image point of view, just the positive quadrant in R2. So this is determined by two functions. Affine function, these are the two normals. So that means x1 greater or equal than 0 and x2 greater or equal than 0. So you start with symplectic potentials of the form 1/2 x1 log of x1 plus x2 log of x2. And now you took care of these two facets. And now you add something that you want to be smooth somehow. Okay? And the point is, since you are looking at cohomogeneity 1 things, you are only going to add something that only depends on the radial coordinate in R4, which here means that only depends on this linear coordinate here. So it's constant on this line. So that means you add something that only depends on what I call there R, which just means that only depend on the sum x1 plus x2, a function of one variable. Okay? And then you write down the scalar curvature of such a metric, and you ask for what are all the h's that only depend on one variable that give rise to extremal Kaehler metrics. That's what Calabi did. So that means that such that the scalar curvature has to be a first degree polynomial. Okay? And you solve it, it becomes an ODE, nonlinear ODE, but you have a change of variables in h. Anyway, the solution is this. These are all the possible, it depends on 4 real parameters, A, B, C, D. and it has this form. The second derivative of h has this form, okay? Which you can integrate, well, for any n. When n is equal to 2, this n is 2. So it's a simple polynomial, and you write the scalar curvature just so that you see the scalar curvature for any such thing of this form is like this. Constant piece plus a linear piece that only depends again on the r, which is x1 plus x2 in this R2 thing. Moreover, you can read off when these things are, of course you can read off when this thing has constant scalar curvature is easy. So this term has to vanish, so d has to be 0. And then you check when are these actually Einstein. Besides having scalar curvature, you have to add the condition that b is equal to 0. And so suppose, so what Calabi did was a beautiful thing. I don't know if you look at that paper, but that paper where he constructs extreme calorimetrics, he has a one-page with just huge algebraic, 4 huge algebraic formulas. So he was actually constructing extreme calorimetrics on Hirzebruch surfaces. And he, given a Hirzebruch surface and a color class on a Hirzebruch surface, he showed what are the values of A, B, C, and D that give you an extreme calorimetric on that smooth Hirzebruch surface. And those were the formulas that you see in those pages, which he did by hand, completely explicit. I'm not going to do that. I'm going to try to find Kaehler-Einstein ones, okay, which are much more restricted than extremal. And if you look at Kaehler-Einstein ones, with this definition, besides the flat metric, you cannot get anything smooth. But you can get, and that's the point I'm making here, you can, for example, get metrics on a polytope like this with conical singularity. So I'll interpret this as having, this is the first Hirzebruch surface. So it's essentially non-trivial S2 bundle over S2 with first term class 1, the bundle. Or, well, there are several ways, but anyway, on a polytope like this, you can build a Kaehler-Einstein metric on this non-trivial S2 bundle over S2, but this, we know that you cannot be the Kaehler-Einstein smooth one. This is different from zero Futaki invariant. There is no constant scalar curvature metric on these things. But you have a Kaehler-Einstein metric which has conical singularities in the normal directions to the zero section into the section at infinity in these Hirzebruch surfaces. And the conical angles are these alpha and beta that I wrote here, and they satisfy some inequalities that you need so that this is a metric, and they are related to each other. So the conical angle in one side depends on the conical on the other side. It turns out that this relation does not admit any pair of rational solutions. So if you pick alpha rational, beta would be irrational. If you pick beta rational, alpha will be irrational. So I found this a long time ago. I never knew what to do with this. So you have some conical angles. I first tried to go to orbifolds, but I needed both of them to be rational. They were not rational, so I never knew what to do. So let me go now to a second part of the story, which is toric Kaehler-Sasaki geometry, and how some other people smarter than me, but in a different approach, made very good use of this. So these are Gauntlet, Martellik, Sparks, and Waldrom, which is a group of mathematical physicists that wanted to build some examples of ADS-CFT correspondence, which I don't know what it is. And then Martelli and Spark, together with Yao, did some extra work, more easy for a mathematician to understand, and also putting this work in action angle coordinates so that I could understand what they were doing. And let me tell you what they were doing. The basic example of what they were doing is here. And this again uses all spaces that I already introduced. So the sphere, here is the standard sphere in C n plus 1, is a contact manifold. Well, it has, so what's a contact manifold? Is something with an hyperplane distribution which is maximally non-integral. In this case, the distribution is just given by the complex tangencies of the sphere in Cn+1. But the sphere has an action, which is the diagonal action of the circle in Cn+1, which acts on the sphere. And the quotient is Cpn, as everybody, I think, knows. And this, although it's such a simple thing, this is a hop map. It's kind of an interesting map. Okay? Also, any contact manifold admits a symplectization, so which is essentially a symplectic structure on that manifold cross R. And here, in this case, of course, this manifold cross R is just the whole Euclidean space Cn+1 or R2n+1 minus the origin. And here you have Cpn, and you have here this diagram, which means from here to here you go symplectization, from here to here you go quotient, usual quotient by the action, and actually from here to here what you have is called symplectic reduction. You go from the cone to the base like this. And this construction from here to up here is also called in symplectic geometry a prequantization. So if you have a symplectic manifold with an integral symplectic form, you can build an S1 action, an S1 bundle over this manifold, whose first Chern class is that symplectic form, and you get an S1 action on the fibers, and this is an example of that. In terms of polytopes, which is what I'm talking about, this is the polytope of Cpn, and this is the polytope you get, the moment map image for this symplectization there. So what you do is that you have some polytope in Rn, you go to Rn+1, put that polytope at level 1 to normalize it, and then take a cone over it. And what I'm claiming is you're doing exactly this. You are going from here to here, and the parameter of this level set is your contact manifold, the sphere. Okay? So, well, I could illustrate, I don't know. I'm fine, but I'm not going to do I'm going. So here is the general picture of what I just wrote there. So suppose you have some symplectic manifold with an integral, the symplectic form defining an integral cohomology class. You can take its prequantization, circle bundle over it, and then that's a contact manifold. And you can take the symplectization of that contact manifold, that's that manifold cross R. And this is also a symplectic manifold. And from here to here you have symplectic reduction, and from here to here you have a quotient in principle given by the S1 action. Okay, but, and you can put the word toric on this so that everything is toric. You can put the word Sasaki. If this is scalar, the metric you get here from this construction is called a Sasaki metric. And this is also a Kaehler cone. And it turns out that if this is Kaehler Einstein with appropriate value of the scalar curvature, this is Sasaki Einstein, and this is Kaehler Ricci flat. This is exactly what happens for the sphere, which is an Einstein metric, Cpn, which is Kaehler Einstein, and R2n+1 minus the origin, which is flat. It's not just Ricci flat, but it is flat. Okay? But now note something here. Suppose instead of starting with a smooth thing here and you do a prequantization, suppose you start with some Sasaki contact manifold. So some contact manifold with some special kind of metric. These metrics come with a vector field which is called the Reb vector field, which is the vector field that gives you the diagonal action in Cn in that other example. If you take the quotient of this manifold by the flow generated by the vector field, you get something down here which is scalar. But that vector field might not generate a free circle action. It might have singularities. It might be dense, the orbits. And so the quotient might be a mess. So you might have a mess down here with a smooth, nice thing here. Okay? It's perfectly possible to have a mess down here and a perfectly nice, smooth thing, Sasaki, Einstein, contact, whatever, toric up here. And this is exactly the situation that happened in those examples of Martelli, Sparks, Waldron, and Gauntlet, those 4 MSG guys. So let me tell you what. So I can move. That's too much. Okay. So what they constructed a new, I think at the time new, these 4 guys, infinite family of Sasaki-Einstein 5 manifolds. They are all diffeomorphic to S2 cross S3. And these are Einstein metrics on S2 cross S3, which are Sasaki. And, well, they are determined by 2 parameters like this, doesn't matter. And they have a Webb vector field, which is actually, does not define a circle action. So only for very particular values of these parameters does it determine a circle action. Even when it does determine a circle action, it's not a free circle action. It has isotropies. In that case, the quotient is an orbifold. But more generally, these guys are irrationally related. The Webb vector field is like an irrational vector field inside a torus, like appeared yesterday in your talk. And so the quotient is a mess. But in this case, what I'm claiming is that the quotient is actually those Calabi Kaehler-Einstein 4 manifolds with cone angles alpha and beta that I talked about. So in the Calabi's family of extremal Kaehler metrics, there were those Kaehler-Einstein metrics with cone angle singularities on the 0 section and the section at infinity of that Hirzebruch surface. And those are the ones that appear as quotients of these new Einstein metrics on S2 cross S3, and moreover you can explicitly say what are the alphas and the betas. So you can recover this whole construction by those explicit methods that I told you about. Okay, so now this is the story I want to tell you about Kaehler metrics of constant scalar curvature, or sometimes Sasaki metrics. These actually give also Ricci flat metrics on the symplectization of these manifolds, on these manifolds crossfire. And I guess from their work, these metrics have some importance in that ADS CFT correspondence, which I don't know nothing about. But now, now let me connect this to contact topology, as I said in the title. So, in this paper, the other paper by Martelli, Sparks, and Yao, where they put these in action angle coordinates, they actually describe explicitly the cones, moment map images of these toric manifolds. They are toric manifolds. And they told you exactly what are the normals. These are cones in R3. So I could even try to, there'll be a drawing of them, I think. But I could even try to draw them. So these are cones in R3 with 4 facets, whose normals are these ones here. Now note, as I said before, that now in this case are the first coordinates of these cones are all 1. So they lie on an hyperplane. So that means that these cones have C1 is equal to 0, as they should, because I told you that these guys give rise to Ricci flat metrics on those cones. That those metrics give rise. So we have a family of examples with first sum class 0. And because the underlying smooth manifold of those examples were S2 cross S3, this gives you a family of contact structures, one for each P and Q, on S2 cross S3. Okay? So contact structures are hyperplane distributions, maximally non-integrable on some manifolds. In these odd-dimensional manifolds, they are kind of the odd-dimension analog of symplectic manifolds. They also arise as boundaries of natural convex boundaries of symplectic manifolds. So they, from the point of view of symplectic topology and contact topology, they are interesting. And so here we have a family, an infinite family parameterized by 2 natural numbers of contact structures on S2 cross S3 that are all homotopic as hyperplane fields. Why are they all homotopic as hyperplane fields? Because they all have first sum class 0, and that in this dimension and for this manifold is the only invariant. So meaning that as hyperplane fields, it's 4-dimensional hyperplane fields on S2 cross S3, they are homotopic to each other. They are the same thing. The question is, for the point of view of contact geometries, are they equivalent as contact structures? Meaning, can we homotop them through non-integrable hyperplane fields, which is a contact structure? So this is an interesting question from the point of view of contact topology, and I came to it because of the underlying contact structures of those Sasaki-Einstein metrics that had appeared. And the story is actually interesting also from the point of view of connections between Portugal and Brazil, because there were some research projects that should designed to make collaborations between Portuguese mathematicians and Brazilian mathematicians. And so, encouraged by Rui Loja Fernandes, who is here, he was going to make a project with Henrique Burstein from IPA, and he said, why don't you come in and let's find someone in Rio de Janeiro who could maybe collaborate with you. And so we contacted Leonardo Maccarini from the Universidade Federal do Rio de Janeiro, who now is also moving to Lisbon. But we contacted Leonardo Maccarini. I had never talked with him mathematically, but we made some kind of project, and it was approved. And at a certain point, he arrived in my office, and he was going to spend a month in Lisbon. And we were supposed to work. And so I came across these contact structures, and he knew a lot about contact homology and invariance of contact structures. So it was natural to try to put our efforts together and attack this problem. And so that started a collaboration that has lasted for 10 years, and not only mathematically, but also we became very good friends and we have collaborated a lot. Unfortunately, he's moving to Lisbon, so scientifically that's great, but from the point of view of coming to Brazil, for me it's not that good because I was coming every year to work with him, and now, so I hope you organize more conferences or something, because otherwise I'll stop coming. Anyway, so sorry for this digression. So let me tell you what's the story. So how much? Oh, I still have. Okay. So I'll give you the punchline and then I'll say some more things. So the punchline is the following. So we started working on this a long time ago. The first paper we published was 2012, but I'm telling you a way of answering this question with a result that was just published this year, although the result is about 1 or 2 years old. And here is the algorithm. So you have those normals of that cone. They all have the first coordinate 1 because C1 is equal to 0. So forget about the first coordinate. Look just at the other 2 coordinates. Now you have a bunch of vectors in R2. Draw them in R2. So if you, here they are. So you take 0, 0, that's one of them, 1, 0, that's another, PP, and whatever this guy is. So 0, 0, 1, 0, PP, and whatever that guy was. And draw this convex hull of these 4 guys. This is called the toric diagram. Physicists, when they look at these things, use a lot these toric diagrams, by the way. So it has meaning, but let me just tell you. And what we've been able to now recently show is that the volume of this toric diagram, the Euclidean volume of this toric diagram in R2, is a contact invariant. And it's not a total contact invariant, it's a true contact invariant. Meaning that if you have 2 of these contact structures with different volumes, there won't be any diffeomorphism whatsoever that will map one contact structure to the other. It's an honest invariant, okay? And you see here, it turns out to be, so if some of you have followed a little bit these developments in symplectic topology and contact topology, there is something called cylindrical contact homology, which you can associate to a contact manifold. It's kind of an homology theory. It has an Euler characteristic, in this case it's a mean Euler characteristic because it goes to if you have a non-trivial homology in arbitrarily high dimensions, so you have to do some Euler characteristic with some salt. You do a mean Euler characteristic, and that's a contact invariant. And it turns out to be equal to the volume of the toric diagram. Actually, it's a very beautiful way how the 2 things relate, but I think it gets out a little bit of the scope of this conference. Anyway, you can see here that in this case, the volume only depends on P, does not depend on Q. Because the variations of Q for a given P are just moving this point along a line here which is parallel to this one. Okay? So that does not change the volume. So the volume depends on P, but it's independent of Q. And so that means that, first of all, you get infinitely many inequivalent contact structures with first Chern class 0 on S2 cross S3, because infinitely many P's. And then, actually, it turns out that for a given P, different Qs, which are not distinguished by this invariant, could not actually be distinguished because one can prove that those contact structures are equivalent. They are not toric equivalent, but they are equivalent. There are diffeomorphisms that map one to the other. Okay? So this was, for me, a beautiful way of seeing how mathematics somehow can be connected from different. So these things appeared from trying to understand the Sasaki-Einstein metrics that those mathematical physicists constructed on S2 cross S3. And to finish, let me just add ongoing work by myself, Leonardo Maccarini, and Miguel Moreira, who is a brilliant undergraduate student, master's student that we have in Lisbon. And by the way, he will finish his master's next year, and he will be looking for good places for a PhD. And he's a brilliant guy. He doesn't need my advertising, I'm sure. He will be looked for. He's an amazing guy. Anyway, so we've been able to show more recently, and that is being written, that actually the toric diagram has much more information than just the Euler characteristic of the cylindrical contact homology. You can recover the full cylindrical contact homology, the rank of all the groups, from the toric diagram, and that is encoded in what's called the Ehrhart. So that toric diagram is an integral polytope. So there is something called the Ehrhart, I can't even pronounce it correctly, maybe it's not even well written, I think it is, but the Ehrhart polynomial of a toric diagram, which kind of counts integral points and then points with fractional 2, coordinates with fractional 2 inside denominator 2 in the polytope, and then denominator 3, and so forth. And the way that count works tells you exactly what are the ranks of all cylindrical contact homology of your contact manifold. And we expect to continue to work in these things in the near future. Thank you very much.
Thank you very much. Are there any questions?
We are certainly interested in that. From the point of view of metrics, those mathematical physicists also have higher dimensional examples that we've explored. The thing is that they also give rise to very interesting contact structures. But the problem from the point of view of contact topology is that in dimension 5, we know that the underlying manifold is always the same, S2 cross S3, which actually is non-trivial. But because in dimension 5 there is some very high-tech classification theorems for simply connected 5 manifolds. And you know that those 5 manifolds are simply connected. And basically those theorems in 5 dimensions says that if a manifold is simply connected, and so normally I say walks like a duck and behaves like a duck, it's a duck. So if it looks homological like S2 cross S3, simply connected, it is S2 cross S3. In higher dimensions, that's not longer true. And so those different contact structures, we have lots of families. It's much harder to see if they lie in the same underlying manifold or not. And then if they lie in different manifolds, then the classification problem, of course, they are not equivalent, because they lie in different manifolds. But on the other hand, from this point of view here, of understanding contact structures in general for toric manifolds, and what kind of invariance can you get, what kind of behavior of cylindrical contact homology can you get, yes, sure, we are working on that in high dimensions.
Any other questions?
About techniques at the beginning, can you use Sasaki metrics for quantum singularity?
Yes, I would think so. We've never went on, we've got the singularities on the quotient. I've never looked at the, but sure, one can. Explicitly, we have to use some homogeneity one argument like, I don't know how to do it. I'm sure they exist, some homogeneity one, yeah. You can construct them explicitly, I think so. But for a general theory, we will need some work like some hard analysis work, and contrary to I think Deleuze, who said, I need to do hard analysis, otherwise I feel I'm not doing anything. You know, I don't do hard analysis. Sorry. I would like to, but I don't.
But could you write down what the hard analysis has to
Well, you want to solve a nonlinear force-order PDE with some conical singularities at the bottom. So it's kind of the Kaehler-Einstein equation or the constant scalar curvature equation in a general setting. So it's in this case, it's kind of a real flavor of a complex Monge-Ampere equation. So you have all the tools, and you even know. So Donaldson's work in dimension 2 that I said proved that understanding completely which compact toric Kaehler surfaces have constant scalar curvature metric. Some of the methods he used there, he also proved interior estimates and things like that in higher dimensions also. So maybe some part of that analysis is already done. But that's already out of my league.
Are there any other questions? I have one more. So these Einstein metrics on this 2 causes 3, I actually studied these before, these physicists from the Einstein context. This generalizes to higher dimensions for infinitely many Einstein metrics on S2 cross S2n plus 1. I don't know if they're contact and also inequivalent, but kind of with the same construction, at least they're Einstein. And you have infinitely many on the same manifold, also in higher dimensions.
Do you know if in higher dimensions if those are toric, if they have a torus action of half the dimension? Actually.
That I would have to think about.
No, thank you very much. No, we know when we mention that there were. I don't think these metrics that mass physics consider are exactly the same ones that.
The Einstein metrics are unique on S2 cross 3. It must be the same ones, I assume.
Thank you.
Are there any other questions? Then let's thank the speaker again.